Okay, so hi there, folks. We're now on our last topic in our module 2 in the divisibility theory and the fundamental theorem of arithmetic. And we talked about this in the very first video of this module, and is this is our last topic, the fundamental theorem of arithmetic. Okay, so we're going to have this as our last topic. Now we continue our study of primes. Okay, we can establish unequivocally the assertion that the prime numbers are the building blocks of all integers. Okay, so the prime numbers are the building blocks of all the integers. And I want you to recall some statements we have talked about videos ago, shall we say. So recall that integers, integers greater than or equal to 2 are made up of primes. That is, every integer greater than or equal to 2 can be decomposed into primes. Okay, so this result is what we call actually as the fundamental theorem of arithmetic, which certainly is, the cornerstone of the branch of mathematics that we're studying today. Okay, this is the cornerstone of number theory. Again, this is called the fundamental theorem of arithmetic. Okay, the fundamental theorem of arithmetic is a cornerstone of number theory. Okay, now also one of its cardinal results. One of its cardinal results of number theory, and it also appears in Euclid's Elements. So it dates back way back in the time of Euclid. So this is the fundamental theorem of arithmetic. So before we can even state it formally and prove it, we need to lay some groundwork first, the foundation of it, in the form of two lemmas throughout. Assume all letters denote positive integers. So just take note, all letters here, all variables. So we say A, B, C up until letter Z, are all positive integers. Okay, so all of them are positive integers. Now let's have for the first lemma. Okay, so the first lemma is if P is a prime and P divides A times B, then P divides A or P divides B. Okay, again, if P is a prime and P is a factor of A times B, so therefore P is a factor of A or P is a factor of B. So let's have a proof of that, shall we? Okay, let's write that as proof. Okay, proof. Okay, so we first start here. So we said here that P divides A. Okay, P divides A. So let's suppose that P does not divide A. P is not a factor of A. Okay, so if that's the case, so we can say that P and A are relatively prime. So then, if they are relatively prime, so maybe we can denote that as the GCD of P and A is equal to 0. Or 1 rather, 1 is equal to 1, since they are relatively prime. So by one theorem, this is a theorem that we did not state. We forget to put it in in one of the videos. So by one theorem, I'm just going to state it here, though we cannot prove it right now. Okay, by one theorem. What is that theorem? Um, Maybe we can make it here. So by one theorem, what is this theorem telling us? So this theorem is actually telling us that um, if okay, if A and B are natural numbers, or shall we say positive integers, are relatively prime, or let's say, oh yeah, that's relatively prime. Their GCD is equal to 1, just like this one. Okay, so Another, I think we cannot use the word if here. Okay, here. Let's use the word let. Let A and B be positive integers. Okay, and they are relatively prime. If and only if if and only if and only if there are integers, there exist some integers alpha and beta, alpha and beta, such that it's a linear combination of A and B. Alpha A plus beta B is equal to 1. Okay, so that's a segue for our theorem, 2 by 1 theorem. Okay, so if we're going to apply this here, since we see that this P and A are relatively prime, so they are relatively prime, so there exists some alpha and beta such that it's a linear combination of this P and A. So let's say um, then there exists some integers alpha and beta in the integers, okay, such that alpha P plus beta A is equal to 1. Okay, it's pretty much the same with the theorem here. So the next step is actually we're going to multiply. Next step is to multiply both sides of the equation, both sides of this equation by B. So let's do that. Okay, multiply both sides of the equation by B. So if we're going to do that, what are we going to have? Okay, what are we going to have? We'll have this one. So we have here, so we have um alpha PB, alpha PB plus a beta AB, beta AB. This one will be 1 times B, so it will be simply B. Okay, so it will be simply B. So by this, from this equation, then okay, P divides alpha PB because it divides P. Okay, it divides P. Okay, and also P divides beta AB because it divides AB. Okay, so again, P divides alpha PB because it divides P, and P divides alpha AB because it divides AB. Okay, so from that statement that I said, since we can say directly, since P divides P, okay, and P divides AB, okay, so by theorem, I think we know this theorem. By theorem 3, rather. So remember the linear combination part. The linear combination part. So by theorem 3, P divides alpha PB plus beta AB. Okay? So P divides alpha PB plus beta AB. Okay? So from that, okay, that is the next step to say here is that is, as you can see, both of them have B's there. So if we're going to get the B out, so it will give us that is P divides B times alpha P plus beta A. So we can see that here, from here, okay, So we can see, or rather, we can see that this alpha PB plus beta AB is equal to B. So since it is equal to B, rather, since it's equal to B, so therefore P divides B. And yeah, this is our end of proof. This is by contrapositive in a while. Okay, so this is the end of proof. We have first supposed that P divides P does not divide A. P does not divide A, but we have only said here that it's an OR. Okay, but in the end, we proven that P divides B. So yeah, that's the end of our proof. P divides B. Okay, so yeah, that's the end of this video. Thank you very much for watching, and I hope that you will like and subscribe. Okay, see you soon. Okay, thank you.